Do I though? Do I? Not really. I just kind of get swept up in here. Section 1.5, inverses and logarithms. So this is the last section out of chapter 1. This is everything out of chapter 1. This is all we're going to review before we start getting into the meat and potatoes of calculus. Section 1.5 is inverses and logarithms. Inverses and logarithms. What we're going to talk about today are how do you find the inverse of a function, and what functions have inverses, what functions don't have inverses, because that's a possibility when things don't have inverses, and the unique properties that a function has if the inverse is also a function itself. So let's take a look here. The book presents this example. Table 1 gives data from an experiment in which a bacteria culture started with 100 bacteria, and in a limited nutrient medium, the size of the bacteria population was recorded at hourly intervals. The number of bacteria n is a function of time, right? The number of bacteria is a function of time. I know time is my independent variable. I'm using that as my x value and saying, okay, as time changes, what is happening to my population? Suppose, however, if we flip that, if that the biologist changes their point of view and becomes interested in the time required for the population to reach various levels. So now my independent variable is no longer time, but it's, okay, I'm going to say how much time does it take for my n value to go from 100 to 168, or from 168 to 259, or from 259 to 358. I don't know why they would set those intervals, but what if we had focused on that instead of just taking it at regular time intervals? What if we set the standard to be the colony population? Well, that is like how we take the inverse. When you reverse the point of view and when you change the variable from one to the other, that's taking the inverse. Okay, that is a n as a function, not as a function of time anymore. This is a population at time t. This is time to reach that bacteria. The number of bacteria is your x value now. Your number of bacteria is your independent variable. The time is what's going to change. Okay. This function is called the inverse of function f. Inverse function of f denoted by f inverse. Remember that this is not like a reciprocal of f in any way. That is just the notation of f inverse. Thus, t is equal to f inverse of n. Okay, and we can interchange them like that. Notice the input of one is the output of the other. The output of one is the input of the other. Okay, that's going to be key here coming up in a second. Yeah. Now, not all functions have inverses. Not all functions have inverses. Let's compare the functions f and g whose arrow diagrams or whose mapping diagrams are shown down below. Note that f never takes on the same value twice. Notice that the function f does not map to the same value twice. Notice that one arrow doesn't go to two arrows don't go to any value in the range. Okay. Whereas g does not make that happen. Take a look at that. Take a look at 2 and 3. Notice how they're both mapping to 4. If that happens, you call the function, if it maps to 2 places, the function is not 1-to-1. 1-to-1, that definition of 1-to-1, which will be on the next slide, is when this happens. When each x value is mapping to 1 and only one y value. Each x value is mapping to 1 and only one y value, and the outputs are only singular as well. Like my arrows are just straight across. There's no cross. It just goes right from one to the next. I'm not having 2 arrows going to the same y value. Okay. Back in algebra, we said, okay, for it to be a function, you can't have 2 arrows coming out of the same x value. But we want it to be reversible. We also want this 4. I can't have 2 arrows going to that 4. Right? That is what's 1-to-1. So that's our definition of 1-to-1. A function f is called 1-to-1 if it never takes on the same value twice. Meaning I never have 2 of the same y values, and that's the notation here, right? F of x1, no matter what the x values are, I don't care what they are, they can be different. No matter if the x values are different, they cannot have the same y value. No 2 y values are produced with one function. Okay, whenever x1 is not equal to x2. Graphically, what does that look like? If a horizontal line intersects the graph of f in more than one point, then we see from figure 2 that there are numbers that exist, x1 and x2, such that the y values are the same. So say here's our splice at x1, here's our splice at x2. Notice that these 2 x values have the same y value. This means that this function right here is not 1-to-1. If you can draw the horizontal line test and it crosses twice, it's not 1-to-1. which means that the inverse function itself is not a function, right? Which means the inverse relation itself is not a function. If I took the inverse of whatever this funky graph is, it would not be a function itself. That means it's not one-to-one, okay? The horizontal line test, a function is one-to-one if and only if no horizontal line intersects the graph more than once. The horizontal line test back in algebra 2, we talked about it as saying, okay, it will test to see if the inverse is also a function. That's what we had said. But now we can use the notation of one, or use the one-to-one phrase to say, okay, if it passed both the vertical and horizontal line test, then it's a function and it's one-to-one. Okay, passing the vertical line test tests whether it's a function. The horizontal line test tells whether the inverse is also a function, which makes it one-to-one. So let's take a look here. Is the function f of x is equal to x to the third one-to-one? Let's sketch it real quick. Okay, let's think about the parent cubic function. This is generally what it looks like, right? First off, that is a function because it passes the vertical line test. Does this pass the horizontal line test as well? Yes. It not only passes the vertical line test, but it also passes the horizontal line test. I can draw horizontal lines till the cows come home, and it will only ever hit once along this graph. That means that x to the third is one-to-one. Yes, it is one-to-one. Because it not only passes the vertical line test, but it also passes the horizontal line test. That means that the inverse of the function, which we'll talk about how we find that in a second, is also a function. The inverse of x to the third is also a function. Okay, what about the parent quadratic? What about x squared? Is x squared one-to-one? Is x squared one-to-one? No, it is not one-to-one because it does not pass the horizontal line test. So my answer to this would be no, which makes sense because when I take the inverse of an x squared, it's a square root. And we have to kind of play with it a little bit to say, oh, we only want the top half of the square root function so that it is a function itself. Okay, so that's because we want to limit the domain a little bit so that the inverse would be a function as well. Okay, if we included both positive and negative root, then look, it's not one-to-one. It's not a function. The inverse is not a function. The definition says that f maps to x into y, then that if f maps to x into y, then f inverse maps y back onto x. Inputs relate directly to outputs. And if we talk about inverses, the output of the regular function is the input of the inverse. Okay? If f were not one-to-one, then f inverse would not be uniquely defined. The arrow diagram that we had seen indicates that f inverse reverses the effect of f. So basically, this is going to happen. The domain of f is the range of f inverse. The domain of f is the range of f inverse. And likewise, the range of f is the domain of f inverse. The domain of one is the range of the other. And the range of one is the domain of the other. Now, whether you're talking about f or f inverse, it doesn't matter. Okay? The domain of f inverse, the inputs to f inverse, are the outputs to f. The outputs to f inverse are the inputs to f. For example, the inverse function f of x is equal to x to the third. We just talked about it a second ago. F inverse of x is equal to x to the 1/3 power. How do we get that? Because it would be the cube root of x, right? The cube root of x. Because if y is equal to x to the third, then take a look here. If I plug in x to the third into f inverse, what happens? It undoes whatever was being done. Look, x to the third to the 1/3 power to a power we multiply, that just gets us back out x. So if my input, if I run it through both f and f inverse, my input becomes my output if it ends up being the same thing. If those two functions undo each other, those are inverses of one another. We talked about this. Don't make the mistake that the f inverse has any, it's not reciprocal. Right? I always have students mess that up. F inverse, that to the -1 power, does not mean it goes down into the denominator. Okay? All I'm saying there is that that's the notation for f inverse. All right, our third example here. If f of 1 is 5 and f of 3 is 7 and f of 8 is -10. So here's my if statement. If all of these things are true, then I want to find f inverse of 7, f inverse of 5, and f inverse of -10. Well, remember, since I was given the if statement, I know that all of those things are true. Inputs match outputs. Right? Inputs of one are outputs of the other. Outputs of one are inputs of the other. So I know in my original function, look at the notation. In my original function, I have coordinates 1, 5. I have coordinates 3, 7, 8, -10. Right? So therefore, this question becomes quite simple. If I switch inputs and outputs, and I go to my inverse and I input 7, what's it going to get me back out? 3. If I input 5, what's it going to get me back out? 1. If I input -10, what's it going to get me back out? 8. Okay? Inputs of f are outputs of f inverse. Outputs of f are inputs of f inverse. X's and y's are going to flip like that. And that statement right there is really powerful. X's and y's are going to flip. That's how we create the inverse function. Right? That's how we create the inverse function. If I want to generate the inverse function, you need to switch x and y and resolve for y. The letter x is traditionally used as the independent variable. So when we concentrate on f inverse, we basically say, okay, I'm going to take in f inverse of x is equal to y. That means that f of y is x. Also, what that means is that if I talk about composition, if I put one inside the other, they're going to cancel themselves out. Right? We saw that with x to the third to the 1/3. If I take x to the third and plug it in, that's going to cancel itself out. Every x value I have in the domain, if I run it through f and then run it through that f inverse, it's going to get me back out what I started with. Okay, those are called cancellation equations, basically saying that everything else will cancel out. Okay, yeah, I can bypass that. This is the important part here. This is how we create our equations. This is how you create an inverse. First step, you switch, if it's a function notation, you take f of x and you make y as your f of x. Second step, and this I might deviate away a little bit. They say solve the equation for x, get x along. You know what I said to you guys back in Algebra 2? I said, okay, switch x and y. Switch x and y. Remove x, plug in y, remove y, plug in x. Flip-flop their places. Then resolve for y. To express f inverse as a function, you just take f inverse of x. I use that notation. So again, what's the process to creating the equation? You take x and y and you swap their places and you resolve for y. And when you do that, you're creating an equation for f inverse. Okay? You use it or inverse operations to solve. Okay. Can we try this? Can we do this? I'm going to pull, I know I still see some people writing, so I'm just going to pull this over here, put it right underneath it. There we go. Okay. Find the inverse function of f of x is equal to x to the third plus 2. A very simple equation to solve. A really simple equation to solve. Okay, my function is f of x is equal to x to the third plus 2. That means y is equal to x to the third plus 2. Right? That's our old. Let's find our new. Okay, I'm going to switch colors for emphasis. And I'm going to say, okay, x is equal to y to the third plus 2. X is equal to y to the third plus 2. That right there is my inverse equation. But to put it in true inverse notation, I need to resolve that equation for y. I need to resolve that equation for y. Subtract the 2. X minus 2 is equal to y to the third. And then how do I undo y to the third? Cube root, right? Cube root the opposite side. Cube root of x minus 2. And now solve for y. So let's put it back into f inverse notation. F inverse of x is cube root of x minus 2. You could have also said x minus 2 to the 1 in quantity. x minus 2 quantity to the 1/3 power. That would have been fine as well. So what was the process there? The process was take x and y, flip them, resolve for y. Okay. I'm going to put another one in here because it looks very similar to one of the ones on the homework. We've got y, let's call it f of x. Let's be formal. F of x is equal to 4x plus 3 over 3x minus 5. Because the trickier we can make the original functions, the more weird things might happen with the inverse. So I've got this rational function, division of two polynomials, right? 4x plus 3 over 3x minus 5. So to find the inverse, we know we can switch this out and say y is equal to 4x plus 3 over 3x minus 5. The weird part about this one is that when I go to flip x and y, there are multiple x's. That's okay, just put in multiple y values. X is equal to 4y plus 3 over 3y minus 5. Anywhere where you saw x, you plug in y. Anywhere you saw y, you plug in x. Okay, so now I solve this equation for y. Remember that the first step in getting y alone here is actually to get rid of the denominator, to get rid of the fraction part about this. So what I'm going to do is I'm going to multiply 3y minus 5. I'm going to multiply it over to the other side. I'm going to take that whole chunk and move it to the other side. So x quantity 3y minus 5 is equal to 4y plus 3. And just move the denominator over to the other side. Let's distribute in the x. 3xy minus 5x is equal to 4y plus 3. Now, I need to get y alone. That means I need to collect all the y values to one side. Let's move all the y values to the left side. I'm going to subtract the 4y over to the left side. So this is going to be 3xy minus 5x minus 4y is equal to 3. And I'm going to move the 5x to the right side. Just to get all the y terms alone. Move the 5x over. So that's going to give me 3xy minus 4y. And on the right side, 5x plus 3. You could say 3 plus 5x, but, it doesn't look weird. Anybody see what I can do with my y values on the left side?
You divide by an x on the other side and then combine them to get negative y is equal to 5x plus 3 over x.
I see what you're thinking about dividing. You can factor it out. That's what we're going to look at. Factor it out. Let's factor out a y. And now I'm going to divide it over. Now I'm going to divide that whole chunk over to the other side. Y is equal to 5x plus 3 over 3x minus 4. That whole chunk brought over to the other side. And now we can just say, instead of y, let's use a fancy notation. F inverse of x is 5x plus 3 over 3x minus 4. Okay, so whenever you have a rational function like that, and you're finding the inverse, you might need to do that whole process of collecting all the y terms, then factor one out. Okay, any questions on that one? Let's take a look here. The graph of f inverse is obtained by reflecting the graph of f about the line y equals x. Sketch the graphs of f of x is equal to the square root of -1 minus x and its inverse function using the same coordinate axes. Okay, I'm going to truly try to sketch this, so bear with me. You know what I'm going to do first, though? Just to see what transformations happen. -x minus 1. I like to flip that around. I don't know why. I just like the x in front. And I'm going to see what transformations happen. Okay, I see two transformations. If I plug in a number here, say I plug in 2, what operation happens on it first? The negative, right? The negative inside. So what is a negative inside going to do? Negative inside. Reflect over the y. Good. Reflect over the y. Then it's a minus 1 on the inside. What's that do? Move to the right one. Okay, so if I've got, I know this is my original parent square root function, right? So look at this. Yeah, presto changeo. Flip horizontally. So it would have gone over the y-axis like that and moved to the right 1 unit. Okay, so now if I want to reflect this over the, and actually, I should say this. Looking up at the top, this is obtained by reflecting the graph about the line y equals x. Where is the line y equals x? It's that diagonal line, right? It's that diagonal line. So now this point becomes up over here, and kind of have to, kind of looks like, oh, that's wrong. That's wrong. Oh, I'm sorry. It should dive down a little quicker, like that. I think. Kind of butchered that a little bit. It's a sketch, but I'm reflecting it over the line y equals x. I'm reflecting it across the line y equals x. I need to go back to my. Should cross where it crosses the line y equals x. I need to draw that a little. Whoa! I need to draw that a little bit better. Get up it. Get up. Okay. There we go. That's a little bit better. Sure. But again, it's a sketch. It's just a sketch. Just a sketch. Okay, now let's talk about the inverses of exponential functions. The inverses of exponential functions. Well, the inverse of exponentials are logarithms. Right, logarithms. I taught you guys, well, I guess me and Mrs. Apple taught you guys for the very first time logarithms. Taught you guys for the very first time logarithms. Logarithms are ones that if you wanted to solve an equation, solve an exponential equation where the variable was up in the exponent, to do that, to find the inverse of that, you need to perform a logarithm. It's basically a new operation. So what does that mean about the base of exponents? Remember, we talked about the base of the exponents in exponentials. It was, we couldn't have any negatives. Same thing is true here. I want the base of my logarithm to not be negative. It got to be number bigger than 0 but not equal to 1. Okay? This is how we transform, right, from logarithmic form into exponential form. Remember, I think we taught you guys like the spiral method. Log base b of y is equal to x, right? B to the y is x. Or log base b of x is y. You can spiral it, and that's what changes the form. Okay? Base of the log is base of the exponent. The logarithm is always equal to the exponent. And the equal to number for the exponent is the of number of the log as well. Okay. A couple different unique properties of logarithms is that if you take the log base b of b to the x, log base b of b to the x, if you ever have the base of the logarithm and the base of an exponent match, like log base 2 of 2 to the x, that will cancel, they will undo each other, leaving an x, because exponents and logarithms are inverses of one another. They will undo each other. So log base b of b to the x will just cancel itself out, reduce itself out, and just become x. That's that whole cancellation equation. Same thing here. Base b to the log base b of x. Do you notice how we have the exponent base and the logarithm base to be the exact same thing? When that happens, when you have a logarithm within an exponent, a logarithm composed in an exponent, then they cancel themselves out, leaving just that of number, that x. Okay, those are just cancellations. A couple other key properties, and I'll talk about that in a second. A couple of the key properties. Remember that if we multiply inside a logarithm, that's addition of the logs. Division inside a logarithm, that's subtraction of the logs. And if I take a power inside a log, I can take this number, that the power, and bring it all the way out front. Okay? These are just the properties of logarithms that you learned all the way back in algebra 2. A couple things about the graph before we move on. Remember that the graph of an exponential had the asymptote. Let me put that back there. I know some people were writing this. The graph of an exponential had an asymptote at the axis. The graph of a logarithm has the asymptote at the axis, but it's no longer the horizontal, it's the vertical. It's no longer the horizontal, but it's the vertical axis. Okay? And just like we saw as we change the base of an exponent, if we change the base of a logarithm, it's going to make it more shallow or more steep, depending on what the base is. If I take that base and make it a fraction, it's going to flip it. If I take that base and increase, it's going to make it steeper and steeper and steeper. Okay. And then, I think this is where we're at. Yeah. Anybody still need those? Yeah. Use the laws of logarithms to evaluate log base 2 of 80 minus log base 2 of 5. Okay, subtraction of the logs means what? What operation? Division. So log base 2 of 80 minus log base 2 of 5 means log base 2 of 80 divided by 5. Okay, 80 divided by 5. 80 divided by 5. 16. And we have log base 2 of 16. Now, we can evaluate that. What is log base 2 of 16? Remember that log base 2 of 16 is asking you 2 to the what power is 16? Well, 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. So this evaluates down to 4. Okay. Nice thing is you guys have in your calculators the log base function, so you can actually evaluate that whenever you want to. A couple other unique things about logarithms. We have natural logarithms. Right? Just like we had e to the x as the naturally occurring constant, Euler's constant, we can put the base of the logarithm as e as well. If we do that, it's got a special name. It's called the natural logarithm, which is denoted by ln of x. Of all possible bases b for logarithms, we will see in chapter 3 the most convenient choice for a base is the number e. And we're going to talk about e a lot in chapter 3. Okay, the logarithm with base e is called the natural logarithm and has a special notation of ln. If we put the base e and replace log base e with ln, we have all of these same type of rules to follow. Just because I change the base into e does not change all of the properties. Like ln of x times y is ln of x plus ln of y. If we have ln of x divided by y, that's ln of x, actually, ln of x minus ln of y, right? If we have ln of e to the x, be careful there, ln is just log base e of e to the x. Remember what I said a couple slides ago? If you have the same base of a logarithm as base of the exponent, that will cancel out. Those undo each other, give you just an x. Same thing here. If you have e to the log base e of x, same exponent base as logarithm base, those will cancel each other out, just leaving an x. Okay? We had those properties just a second ago, and now, since I said we could use it with any base, if I change the base to e, that doesn't change anything about those rules. Okay? Same thing with my transforming from one to the next. ln of x is equal to y is basically like saying log base e of y, exponent base e of to the y is x, right? Spiral it. Right? E to the y is x. So both of those things are inverses of one another. Okay? And another thing, ln of e is 1. ln of e is 1. The natural log of e is always 1. Why is that the case? Because this is like saying log base e of e is what? Right? Like if we were not sure about what that thing is, isn't that e to the first power? Doesn't all of that cancel out, right? Log base e of e. So that means my answer is just 1. This actually equals just 1. You could do that for any base. Log base 2 of 2, 1. Log base 7 of 7, 1. Log base pi of pi, 1. Any logarithm base. Let's solve this equation. Find x if ln of x is equal to 5. So from here on out, we're just kind of using the operations of logarithms to solve some equations. Find x if ln of x is 5. You're going to find that when you're working with equations, it might be easiest to change ln into log base e. I don't know, that's just what I always did. So log base e of x is 5. Okay, now I can spiral it. I can say e to the 5th is x. And I just solved that equation. What is x? It's e to the 5th. Because e is an irrational number, just like you write things in terms of pi, you can write things in terms of e as well. It's totally acceptable to say x is e to the 5th. Could you actually figure out what that is? Sure. E to the 5th, that's this number. Right? That's just that irrational number, 148.41 and so on. Okay? But it's totally acceptable to leave it in terms of e if you'd like to. Let's take a look at the next one. Solve the equation e to the 5 minus 3x is equal to 10. E to the 5 minus 3x is equal to 10. Okay, if I want to solve an exponential equation, solve for an exponent, that means I need to turn it into a logarithm. All right, so if I want to do that, let's spiral this. It's already set up in exponential form. Let's spiral this. Log base e of 10 is 5 minus 3x. Everybody follow me there? You're going to get used to changing from logarithmic form into exponential form. Log base e of 10 is equal to 5 minus 3x. Well, that's just ln of 10. And I can just take in my calculator ln of 10. It's pretty simple. 2.3, let's put it as a decimal. 2.3 is equal to 5 minus 3x, rounded. Subtract the 5. Negative 2.7. And we divide by negative 3. 0.9. Rounded, approximately 0.9. Okay, so I will stop there for today. We've got 1, 2, 3, 4, 5, 6 slides tomorrow. So I'm hopefully going to give you at least half the period to work on your assignment tomorrow. In my memory, those go quick, so hopefully they do tomorrow as well. Your assignment is kind of a little bit heftier. Sorry. So tomorrow, I'm going to give you a good amount of time to work on your assignment. And then on Thursday, when you come in, it's all fair game. Any questions that you have on any assignment, I can answer them. And then I'll give you a take-home quiz to work on after that. Sound good? Okay. Got to remember to stop videos. Last time I had a video that was like an hour and a half long. Whoops.